All right. Well, I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for the weekend, for time to relax and maybe get caught up, refreshed, and just pray that you be with us today. Help us to glorify you in what we do, and just understand a little bit more about why Green's theorem is true, and also how to use it, Lord. In your name I pray, Lord Jesus. Amen. So let's see here. We have last time I motivated for you guys, I hope, why there's such a thing as Green's theorem by looking at a little rectangle and making a kind of funny argument, and then we added that up infinitely many times and used properties of the integral, and out popped the Green's theorem. And then I made a substitution to get us to this form of Green's theorem, which is pretty much the standards form. Says the integral of p dx plus q dy over some region is equal to the double integral. This is the boundary of the region, rather. Over the region of partial q, partial x, minus partial p, partial y, dA. All right. And so, for the time being, I want to give you guys a proof of Green's theorem in the case that the region R is both a type 1 and type 2. So let me just write down what that means, all right? So here's a proof assuming R equals to, on the one hand, all x and y such that A is less than or equal to x is less than or equal to b, and f1 of x is less than or equal to y is less than or equal to f2 of x. All right. And also, it's simultaneously equal to x comma y such that c is less than or equal to y less than or equal to d, and g1 of y less than or equal to x less than or equal to g2 of y. Now, in actual problems, I tend to give labels to these functions that I just threw up on the board here. That doesn't sound good. So like the y base or bottom, this is y top, right? This is the left x, this is the right x. If we can simultaneously find a left, a right, and an up and a down defined in one foul swoop by a function, then it's a type 1 and 2 region. All right, so like, see if I can draw a picture of this thing. Excuse me. So something like, so you've got C, D, A, B, and looks kind of like a lemon or something, I don't know. So you've got this point. Wait a minute. Yeah. Wait, what? Oh, I'm not sure I entirely believe that my, oh, right. Is that it? Well, let's have it drawn. So, anyway, certainly there are regions that are both type 1 and type 2. But the larger point is, if this is the case, then we can picture, C1 down here, right? And as I have it labeled, C2 up here, right? And C1 union C2 is the boundary of the region R. And I haven't, well, shading is always kind of shady. on these whiteboards, but here I'll use my orange. So R is this region all together in here, okay? And notice that the boundary of R is the what? It's the counterclockwise oriented outer boundary, okay? That's what that is. All right, so getting to the point here, eventually, we can write, we can parameterize C1 and C2 by what? Well, like C1, we can parameterize like this. We can write R1, we can use X as a parameter, right? And we can do like X comma F1 of X to get C1, because see, that's the lower. So what I'm going to do is I'm going to calculate part of Green's theorem in this proof, and the other half is left to you guys in homework, which I may or may not have assigned. I can't remember. Did I sign it? Don't think so. Oh man, I'll put it on the quiz. I'm kidding, probably. And then minus C2, R2 of X is equal to X comma F2 of X. Notice why I did, listen guys, the reason I did minus C2 is because C2 goes from right to left, right? So it's just more natural, if you want to make contact with Cartesian formulas, to use Cartesian variables as parameters. So it's just a better choice for what follows to look at minus C2 as the parameterization. In my experience, that's a good move. All right, so the proof of the theorem can be split into proving two results. Basically, this is equivalent to proving two things. We need to prove, on the one hand, the integral over the boundary of R of p dx is equal to the double integral of partial q partial x dA. Oh, my bad. Partial p partial y. That's not how it works. Partial p partial y. And there's a minus on this guy. And the integral over the boundary of R of q dy is actually equal to the double integral of partial q partial x dA. All right. And we'll just look at the proof of the p part, but the proof of the q part follows by a very similar calculation, all right? And so here's how it goes. We start with the integral over the region, the double integral of partial p partial y dA, all right? Now, from this point on, it's pretty straightforward once you got all this set up. It's really just like fundamental theorem of calculus. It's very much like the proof we did the other day to construct the potential for the vector field. It's kind of the same math. So if this region is set up as it is, well, how do I break this integral down into an iterated integral? How's it go? We do what? We integral of what? If we're going to do, we'll use the type 1 setup. So we use a to b. Integral from f1 of x to f2 of x, all right? And then we're supposed to do like partial p, partial y of what? Of, well, x comma y. And which integral come first? Nope. So 50-50, right? Yeah. Yeah, that's good. So this right here binds us to dy, and that binds us to dx second, right? Because the outer bound is the inside out, right? Okay, so look at this inside integral. What you got? What you up against here? Right? Yeah, fundamental theorem of calculus part 1 or 2, I mean, however you want to look at it. But, so we've got an antiderivative of p. It's partial p, p is the antiderivative here because we're integrating with respect to y. So what we get then is p of x comma f2 of x, right, minus p of x comma f1 of x, using the, like you said, the fundamental theory of calculus. All right. Then what? Well, then let's break it into two integrals. On the one hand, we have the integral from a to b of p of x comma, f2 of x, right, times dx dx dx, and then minus the integral from a to b of p of x comma f1 of x dx dx dx. I'm just doing that to emphasize that this is one of those integrals over the differential. Like, remember we had to like dx dt times dt, but when t equals to x, that's what it looks like, right? So you're just looking at a line integral. This, let's see here, what parameterization are we on there? See that? It's minus c2. So we're looking here at the integral over minus c2 of p dx plus the integral, that one, yowzers. Oh, well, that's good. And so minus, rather, if I write my minus. Actually, the minus is good because that's what we want, p dx there, right? So altogether, we've got minus the integral over c1 union c2 of p dx, aka minus the integral over the boundary of r of p dx. There it is. Well, there's half of it, right? How would the other half of the proof go? Right. Yeah, so you do the partial q partial x, start with the double integral. You don't want to use the type 1 setup for the other way. You want to use the type 2 setup for the opposite way. And so when you do the type 2 setup, you end up with the x integral first. You apply the fundamental theorem of calculus. You do the same thing, and it breaks up. Now, now for the other way, you won't use the same c1 and c2 either, right? For the second, the other half of the integral, you would instead look at curves that go like, instead of using these two anchor points, you'd use like these two anchor points, so to speak. It would be like, this would be my C1, right? And that would be my C2. Something like that. And then I'd be able to integrate from, C to D, and then see, on this would be the, this equation right here, this guy is my G1 of y, x, that's my XL over here on the left, and that's my XR on the right. I don't think we've ever really had an example quite like this, but this could happen. Oftentimes for us, the left and the right and the up and the down, they end up joining at the same points just because, I'm not too mean. But it's easy enough to come up with an example like this. Like the extreme case would be this, right? Well, it's not really extreme, but an easy thing to think about. How about a circle, right? You have the top and the bottom joined here and here, right? You have the left and the right joined here and here, right? And certainly if this circle wasn't centered at the origin, it would be easy for those points to be, different magnitude as well. All right, enough. Any questions? If you haven't, you should read the announcement I made, right? So like, for example, we're not having a quiz this morning. Yay, right? Yay? You guys seem disappointed. I could still make one up. No? Okay. I figured the quiz would probably be more productive if you spend a few more hours on the homework, which is due when? Thursday, right? All right, so there's that. The next thing I should talk about is holes. What's the deal with holes? So if we had something, I'll start with one hole. like this is a hole. And so I want to talk about what's Green's theorem look like over a region that has a hole in it. Can we still do Green's theorem? What's it look like? All right, so here, the shaded part, all right, is what I'm going to call R, all right? And here's our convention. The boundary of R is equal to the, let's see here, C out, the outer boundary, C out, which is counterclockwise oriented, unioned with inner boundaries, which are going to be clockwise oriented. This is the so-called positively oriented boundary of a region. So you're like, well, I don't know what's inside and I don't know what's out. Okay, fine. Here is a simple thing we can do. For points on the boundary of R, if we walk in the direction of the boundary of R as a little dude, R is on the left. So imagine yourself a little dude. And he's walking along the boundary, right? And he has to walk on, he's not behind the board, he's in front of the board, all right? But he's walking along the boundary. See, if he's walking this way, it's on his left. Can you see that? And that's still true when he's up here, right? Still on his left. And if you can picture Mr. Top Hat in here, right? If he's going this way, the inside of the region is on his left. So in short, that summarizes by saying we take outer boundaries and we make them counterclockwise, and we take inner boundaries, we make them clockwise. All right? And of course, there could be more than one hole, right? You could have multiple holes, same idea, right? So like basically the outer boundary is counterclockwise, the inner side boundary is clockwise. Oops, clockwise. Hold on a second. I have trouble sometimes with clockwise and counterclockwise, as you can see. Let me, just a second here, let me think. I need more clocks in my life. Yeah, clockwise. Yeah. Sorry, this is, you gotta watch me. Clockwise, yeah. Sometimes I just don't know what time it is. Maybe I made these mistakes on purpose so I could say that. We could think that, right? That's an allowable interpretation of this lecture. But anyway, if you have them lining up like that, they ought to be going in opposite directions if you're inside and out, all right? Yeah.
With an island in the hole, it goes in the direction as the outside of them?
If you had an island, ooh, that's very interesting. I never thought about that. But yes, if we had an island, that's a great question. If we had an island in the, oh man. All right, so yeah, if I had a little, then that one, because again, the rule is if you're a little dude, it would have to be, the dude rule is like universal, dude. But yeah, I think that would again be, that's a really interesting point. I had not thought of this before, Sam, but you're right. Did I do it wrong? I did it wrong. Son of a gun. I meant to put counterclockwise. Let me think for a second. Yeah. Yep. Goodness. I had not thought of that. Cool. All right, so anyway, yowzers. Man. God. Now I'm trying to think of how to. So here's what I'd like to do the proof for. Because I think if we can do the proof for this, then we can adapt it for the island one. Although I'm worried. But listen, guys, all you do is this: take this. So suppose the region is as pictured. Okay, so we've got the hole in the middle, and we've got this is our region. All right. So what you do is you just throw in a couple of what are called crosscuts. All right, to try to prove Green's theorem on this thing. So all right, so I want to have positively oriented, so it's counterclockwise up here, right? Clockwise down here. Clockwise, yes, clockwise. And so I throw in some crosscuts here. They're called crosscuts. So I'm illustrating it as if they're two separate lines, but really think of this as the same line and its reversal. So up here, we're going like that and like that. But down here, we're going like this and like this, okay? But they're the same set of points. What I'm doing is I'm basically taking a pineapple slice and chopping it so it's two half slices, right? So to speak. And once you do that, then if we have, let's call this, if I call this region 1, and I call this region 2, and if I look at the integral over the boundary of region 1 of f dot dr, right? Plus the integral over the boundary of region 2 of f dot dr. Well, I just have the integral over the union of the regions, right? Which, by the way, would just be equal to the integral over the boundary of the union of the upper and lower half, right? Do you agree? Do you see why the crosscut, the new edges, the blue edges on R1 and R2, they don't contribute anything to the integral over the whole boundary of the union of the two? See, because it's the same set and it's reversal, so those just cancel out. But that's great because each one of these guys we can separately, and let's, I'm using my usual notation, F equals to PQ, right? F equals to PQ. And so on each one of those half annuluses, right? Half of a pineapple slice, if you like. Those cored pineapple things you get in the can, the horrible tasting ones, what I'm talking about. Anyway. When you pay good money for pineapple at a restaurant and then they give you that, you're like, I've been cheated. Anyway, so on the one hand, we've got the double integral over R1 of partial q, partial x minus partial p, partial y, right? And then for this guy, we've also got over R2 of partial q, partial x minus partial p, partial y, right? But then you can, of course, add those together, and when you integrate over two subsets, and then you take the union of those subsets, that's the integral over the totality, using the additivity of the integral. So this is really just the integral, double integral over R1 union R2 of partial q, partial x, minus partial p, partial y, dA. And then, of course, to complete the somewhat circular proof. This is an example of a good circular proof, though. This is equal to that, then. In other words, I can take the integral over the whole region, I can break it up into a sum of the integral over the top, plus the integral over the bottom, if I start with a line integral. And then I can apply Green's theorem to both halves separately, because there's no holes for the halves. And then I recombine by properties of integrals to get Green's theorem with a whole. So what's the long and short of this is that the Green's theorem that I wrote at the start of class is still true. I sold the one at the start of class as Green's theorem with no hole, but the fact of the matter is that the induced orientation for the boundary notation automatically treats the case of the hole through this convention that we orient the inside part clockwise. Any questions so far? Now the question is, how can I use that to prove this? I mean, first of all, let me redraw that in a less onerous way without the dudes. Let me draw Sam's without the dudes. So it's basically this. We've got one hole here. We've got a bigger hole over here, and we've got an island. So how can I use the cross-cut idea? I guess I can basically cut it into here and here. And then I can cut it here and here and here and here if you like. Right? Then I'll have like this region, this region, this region. And then I think this is just the fourth region. And basically I apply Green's theorem to each one of these separately and then add it together and we get the result. Because I can already apply Green's theorem here directly because it's just a simple shape with a counterclockwise oriented outer edge. So this already falls prey to our initial derivation. I don't even need anything fancy there actually. And the rest of it we treat with the crosscut idea, breaking it up into little, either little pieces that we can apply Green's theorem without a hole for. Okay, so lest I forget, there's something even more important. Well, I don't know if it's more important, but it's super useful. Deformation theorem. Check this out. If partial q partial x is equal to partial p partial y on region bounded by counterclockwise curves closed, C1 and C2, then the integral over C1 of p dx plus q dy is equal to the integral over C2 of p dx plus q dy. Here's the proof of that. So what I'm saying is you've got basically here's your C1 and here's your C2 and here's your C1, right? And in between those you have partial q partial x equals to partial p partial y all up in here, okay? So what can we do? We can apply Green's theorem. So I'm going to call that region R. R. And we have that the integral over the boundary of R of p dx plus q dy is equal to the integral over R of partial q partial x minus partial p partial y. But what is that? By assumption, the partial derivative of q with respect to x and the partial derivative of p with respect to y, they're equal between these curves in that region, R as I've labeled it, in that annulus. So that's 0 because this is 0. The integral of 0 is 0. But on the other hand, the boundary of R is what? Well, it is C2, as I have it written at the moment, union with minus C1. Because C2 is, wait a minute. What have I done? Is it clockwise? I've drawn clockwise or counterclockwise at the moment? Clockwise. Great job. But the truth is that this is true for either clockwise or counterclockwise. However, if I write that, I need to put the minus on C2 and leave C1 well enough alone because it's a clockwise oriented inner curve, which is allowed, in fact, demanded by the notation partial r. So long story short, this is the integral along minus C2 of p dx plus q dy plus the integral over C1 of p dx plus q dy equals to 0, which gives what? The integral of f dot dr over C1 is equal to the integral of f dot dr. And you can see that this proof is easily adapted in the case that they're both counterclockwise, right? What does this all mean? Aw, man, I've lost my juice. Where's my juice gone to? Sadness. The juice is loose. I think I left it in the big room over there. I hope it's still there. So you guys remember we did that example, and Sam was like, oh, but the partial q partial x is not equal to partial p partial y, right? And then I was like, oh, no, I disagree, it is. And then we worked it out, and we found out, yeah, it was equal, right? Remember that? What was that example? So, yeah, it was d theta, that's right. So specifically, it was this vector field, right? Minus y over x squared plus y squared, x over x squared plus y squared. This is my favorite example. This vector field here has many curious and beautiful properties. Now we have calculated that the integral of this, right, over the unit circle was equal to, remember we worked it out, it was 2 pi, right, C1 unit circle. We have also checked for this one, right, so we've also previously calculated, right, here's P, here's Q. We have checked that partial q partial x is equal to partial p partial y on where? Actually on R2 modulo the origin, right? On the punctured plane, it's true. This we've also checked. So consider the following. Here's my unit circle, and I'm going to counterclockwise orient it. Ah, man, I am the worst with the orientation today. There's a joke there. Let's see here. I'm not going to say it though. Let's see here. This way. There's my unit circle, right? Consider this. I could take a curve like this. Right? Also counterclockwise oriented. If that was C2. And what's the integral? What's the integral of f, the same f, along C2? Two pi. Yeah. And that's true no matter how big, like, I mean, it's just really, really neat. No matter how big that curve gets, as long as it's encircling the origin, right, it's going to work out to 2 pi. Because partial q partial x is equal to partial p partial y in between, right? Another way to look at this, remember, is that the curl of f, if we think about it three-dimensionally, the z component of it was equal to 0, right? So another way to see this is that we've got this deformation theorem when the third component of the curl is 0. And I think there's also a way to look at this in terms of divergence. But anyway, let's focus on this much here for now. Let's look at example 2. So in some sense, I'm sorry it took me so long to get through the proofs. In another sense, I'm not sorry because the proofs here contain important calculational ideas, especially this idea of inside and outside orientation. That is so important for success going forward here. In what we're doing, we must keep in mind this orientation idea. And it's going to stick with us, like this concept of orientation. It's also going to be a big issue for surface integration, which will start tomorrow. Let's see here, example 2. Let us just do a plain old Green's theorem example. Suppose you've got this triangle here, and so we're going to say that this point is the origin, this point is 4, 0, and this point up here we'll let be 4, 3, okay? And I'm going to orient them in the usual counter clock. Wait a minute. It is okay. Thank you. I have problems. And let's say that, you know, this region is t, and we would like to calculate the integral over the boundary of t of, let us say, x squared plus y dx minus xy dy. I think we can all agree that we don't actually want to do the line integral, right? I don't. If I had to do the line integral, I'd have to break it up into 3 cases. The base, the vertical leg, and the hypotenuse, right? Like, that'd be a pain. So it is much better to switch this over with Green's theorem, right? Green's theorem says, aha, this is my p, this is my q, and so this would be the double integral, right? Partial q partial x is minus y. Minus partial p partial x is what, 2x? So we just got to do this, right? Did I do it right? Double check me, please. If I made a mistake on the partial differentiation, or if I omitted a sign or something, I'd love to know about it now. Okay, so now you guys, if I did that right, how do I set up this integral? Yeah, I think type 1's a good idea. So we'll do 0 less than or equal to x less than or equal to 4, and then how about y? I mean, 0's down here, right? What's the equation of the line segment that goes from 0, 0 to 4, 3? I've got a vote for 3/4 x. Let's see, do we believe it? If I plug in x equals to 4, I get 3. And if I plug in 0, I get 0. Cool, we got it. So integral from 0 to 4, integral from 0 to 3x over 4 of minus y minus 2x dy dx. So that's integral from 0 to 4 of, let's see here, minus 1/2 y squared minus 2xy evaluated from 0 to 3/4 x dx, which is the integral from 0 to 4 of minus 1/2 of 9 over 16 x squared minus 6 over 4x squared dx, which is like minus 9 over 32 minus 3 over 2 parentheses times the integral from 0 to 4 of x squared dx, which is like, you know, minus 9/32 plus 3/2 times 4 to the power 3 divided by 3. So yeah, whatever that is. So there's an example. Example 3. What if we have the double integral of dA over x squared over a squared plus y squared over b squared less than or equal to 1? So this is a kind of typical way you'll see in various books and so forth of writing a double integral. Just you write the condition that defines the area under it, right? Now, at first glance, you might not see this as a Green's theorem problem. So here's where there's a trick, all right? So like, so you guys tell me, if I want, suppose I want partial q, partial x, minus partial p, partial y, right, to be equal to 1. How can I make that happen? You know, to get this, let me start us out. Here's 1. What if we do 0, 1, 0x rather? If I do that for my vector field, what's partial q, partial x? It's 1. But partial p, partial y, 0, that works, right? What else could you do? You could do, well, if you get this trick, how about this? Minus y, 0, right? You could do that. Anything else? What if you wanted to go halvesies? You could look at the line integral of like minus y over 2, x over 2, right? These are all options. You could look at the line integral of any one of these 3 vector fields to calculate the area. So I'll tell you what, I'll use the first one just for the sake of specificity. So this, look, is really the double integral over partial x of x minus partial y of 0 dA. See that? And I'm going to call this thing E. You're like, we've done this example before. We don't know how to do this. Well, that's true, but I'm showing you another way. And so then this is the integral over the boundary of E, also known as an ellipse, of what? X dy, right? Okay. And how do we parameterize the boundary here? We put x equals to a cos t, y equals to b sine t, 0 less than or equal to t less than or equal to 2 pi. And so this gives us integral from 0 to 2 pi of like a cos t. What's dy? Well, b cos t dt. Aha. So we've got a b integral of cosine squared, also known as 1/2 of 1 plus cosine 2t dt from 0 to 2 pi. And then, of course, the cosine piece integrates to 0 because it's integrating a sinusoid over a complete multiple of its cycles. So this integrates to 0, and that guy integrates to pi, well, 2 pi over 2. So we get pi a b is the area of an ellipse. Now yeah.
How do you know that line integral equates to the area of that? Or why were you
Because I wanted to show you how we can use Green's theorem to calculate area.
Or how do you know they're equivalent?
Well, this is one. It's a trick. Now there's other tricks, like you could have used minus y dx. And if you look at minus y dx, you can see from what I've written on the board that if we had chosen to integrate minus y dx, we would have gotten what? I think the same thing, but with a sine squared, right? If we use the same parameterization for the ellipse, we'd have got a sine squared integral, but it would work out the same, pi ab. If we chose the mixed one, not sure what would have happened. Maybe we would have got like sine squared plus cosine squared. Maybe this would have been the easiest in terms of integration. Like if I wanted to make this more impressive, I probably should have done this one, because it's symmetric with respect to the ellipse. So, any questions? Well, there's a question. Now there's a super neat example in the notes where you can work out basically you can work out the integral from if you work out the integral from x1 to x1 y1 to x2 y2 of like, let me make sure I write the formula down right. Of 1/2 x dy minus y dx, and you can work it out. This works out to 1/2 of x1 y2 minus x2 y1. All right. So like here's example 4. So this is a simple exercise. You can work out that the integral over the line segment of that vector field is that. But Green's theorem says what? Green's theorem says that the area, right, is also equal to the integral of like 1/2 x dy minus y dx, right? Over the region, the boundary of the region. So if your region is like a regular, polygonal, it's like if it's got flat sides and line segments like that, right? You can just add those up as you go around the polygon, and you can get the area of a polygon by taking sums of these things. There's like this super sneaky formula for the area of a polygon just by this particular addition of the corners. This to me is one of the most sort of dark, mysterious applications of Green's theorem, but it's very cool. And probably it predates calculus in all likelihood. I bet Heron's theorem? That sounds, I'm sure it has a name. So anyway. Well, so tomorrow we have a quiz on integration, like line integration, conservative vector fields, and then we'll go on to surface integrals. So thanks guys.